Okay. Hi, everyone. My name is Maria, and today I'll be presenting a proposal that was a joint work between myself and David Crapis from the Robust Incentives Group. But before going to the actual proposal, I want to first start by building a shared understanding of gas in DVM. In this case, gas serves two main purposes, okay? So the first one is that gas is used to measure consumption of resources in DVM. So the more a transaction uses, the more it should pay in fees. And so gas is this measure that allows us to let's say, measure the resources consumption and then charge users for it. And we can think of it as transaction pricing, right? Like we are using a model that tells us how much the transaction costs to execute. On the other hand, we have this sense of a function of controlling resource abuse. And by this, we are essentially trying to use gas as a way to tell us how full a block is and how far are we from reaching safety limits of the network. So given a block, how far is that block of reaching certain limits that make the network unstable in some way. And currently, validators enforce a limit of 36 million gas. And if a block goes above that gas usage, then that block is not valid. And we can think of this function as block metering, right? Like we are metering the resources and making sure that we are not going above unsafe limits. Since both functions have been together for so long, so we've been using gas for a long time to describe these two functions, it's natural to think of them as the same thing. And so every time there's proposals to change either the metering or the pricing, we tend to bundle these two together. And our argument is that they are actually separate things, and there's some gains to be had by considering them separately and maybe changing just one of them and not the other. And this is what this proposal is about. And so this is where we go to the multidimensional metering. And so as the name indicates, we are only focusing on the block metering. So we will not change anything related to transaction pricing. We are really focused on just introducing a new mechanism for metering. And the proposal is very simple. So we are just introducing a key change, which is introducing this new variable that is the gas metered. And the way it works is that during transaction execution, we will be tracking, instead of tracking a unique measure of gas, now we are tracking a vector of gas usage, and each dimension will be a resource. We can have compute, state growth, memory, storage, etc. And we keep this vector, right? We are summing the costs at each resource. And then at the end of the block, essentially the gas metered is just the maximum of the various resources. So you can think of these max as like, we are just saving or taking into consideration the bottleneck resource. What is the resource that is being used the most? And we still keep the gas use, which was the previous metric. And the gas use is just the sum of everything, right? Like we are just measuring how much gas across all the resources is being used by the block. And so at transaction level, everything remains the same. The user still just gives you a single limit, gas limit for that transaction. The fees work the same. You are still paying the same fee that is computed over the sum of all the resources. And the out-of-gas validity condition is also the same, so it's considered over the sum of all resources. But then at block level, this is where the changes start. So, and there's two main. So first, we are using the metered as the block validity condition. So this means that when we are verifying if a block is full, so it's going over the limits, then we use this max formula, okay? And then we also use this formula for the base fee update. And this means that if the bottleneck resource, so the resource that is being used the most, is going over the target, then the base fee will increase. If it's under, the base fee will decrease. So now instead of just summing the resources, we are just using the bottleneck resource, okay? And to illustrate, let's go over an example. So imagine that we have a simple block with just these two transactions, and we are just considering two resources. So we are considering compute and state growth. In transaction 1, we have a state growth cost of 8 million units, and for compute, 10 million. Transaction 2, we have 12 million units for state growth and 6 million units for compute. So at transaction level, again, everything remains the same. So the gas used for transaction 1 is 18 million. For transaction 2 is also 18 million because we are summing over the resources. The base fee is the same. We are just multiplying that sum with the base fee for that block. So fees remain the same. And then at block level, the gas metered, so the formula we are using to define how full a block is now using the max over the resources. So for state growth, we are summing the 8 with the 12, so we get 20 million units. And for compute, we get 16 million units. And so the max of it now is 20 million. And so this arrives at the block utilization of 55%, so a little bit over the target. And so there will be a slight increase on the base fee. But if you think about it, if we were in the previous model, the update and the block utilization will be over the sum, so we'll be at limit at 36 million, okay? And so base fee would increase more. Okay, so now we should discuss why even consider this change and why does this make sense. And I think there are mainly 2 points. So first, doing it like this, we are aligning, we have a better alignment between what the block utilization is and actually how far are we from the limits that we set ourselves that the block should have. And then as a consequence of that, we get more efficient block packing. And I think this is the part that may be more interested for block builders and the audience here, let's say. But let's first go with the first part. So for the better alignment, we need to discuss how we actually set these limits, like how do we arrive at the block limits as they are and the costs of the opcodes and EVM operations as they are. And the general idea is that at each resource, we sort of have some gold limits that we don't want to pass. So for instance, for compute, we could say we don't want block execution to take more than 3 seconds. And there are some standard hardware setup. And for state growth, we could say we don't want a block to increase state more than 14 kilobytes, for instance. Once we have these limits, we can map this into the gas limits. And the way we do it is essentially we create benchmarks where we see for each operation, each EVM operation, how much these operations are spending at each resource. And then we can map that to the units, assuming that there's, if we had a block, for instance, full of add operations, and that would take the 3 seconds at block limit, we can then see how many adds we would need to have, and then do the mapping to the the gas costs. Okay. Okay. So on this alignment thing, so let's now think about another example here. So we know that there's this mapping between the limits from a resource perspective, so the seconds for compute and the kilobytes for state growth. And we have a mapping between that and the gas units. So in this example, for instance, if we had these two transactions where one of them only uses compute, the other one only uses state, the total in the current model, the total of usage would be the 36 million units. So we would be already at the limit, right? But if we think about it, actually, this block is not at the limit in any resource, right? Like for state, we are just half, and for compute, we are also just half, okay? And so now with the two-dimensional model, where we use the max, we are actually just considering the bottleneck resource. And in this case, they are both the bottleneck because they all have the same spend. But essentially now with the max, we get the 18 million, which is exactly at 50%, which aligns much better between how far the block is to reach the limits from a resource perspective and the gas metered, okay? And this is also the reason why actually this also helps with efficiency, because now we are metering the resources much more accurately. We can actually pack blocks more efficiently as well. So with the same block limit, we can actually add more transactions without going over the limit safety limits. And show this, we did an empirical analysis where we looked at historical blocks. And essentially, we mapped between transactions and the costs, the gas costs for the different resources. And then we did a breakdown of the blocks into the various resources. And this is what you can see here. It's like for 6,000 blocks. And each small column there is just an aggregation of 10 blocks. And we can see that the more used resources on average are the state, which is the state growth, access, which is storage access, so read and write, and compute. And they are all more or less distributed like a third, a little bit less than a third in each. And then the other resources are more minimal. And so this means that there are gains to be had in doing a four-dimensional model where we separate at least compute, state, and access in their own buckets, and then we could have a bucket for all the others. And what does this gain look like? So we did also a simulation where we kind of assumed that we would have infinite demand of historical transactions. And then we would fill the block in a first come, first serve to make it simpler. So we didn't do any optimization or trying to pack it more efficiently, let's say. And this is, you can see here in the table, the gains in throughput, so the number of transactions, and the gains in the gas used for each model. Okay, so we have, for instance, the first is just you isolate, compute, and then you sum all the resources in its own bucket. And for the last one, which is the four-dimensional one, we can get an increase in transaction throughput of around 240%. So based, again, on historical usage patterns, if transactions change and that use a slight different allocation of resources, this will also change, of course. Then this gives you a sort of idea of, at current blocks, what efficient packing could mean, so in terms of more throughput. So there's some benefits to do this more efficiently. So what are now the next steps? So a big one is benchmarking resource usage per operation. So that table I showed you before, where I said, like, how do we actually go from limits in resources to gas units? This was done initially when the EVM was being built, and it was not done with the clients we have right now because they were not built yet. So it's kind of fundamental now to redo that analysis and make sure that we have a proper breakdown between the different operations and the cost per resource. And that relates then to the final gas cost of that operation. This is something we are working on at the moment. The other one is, of course, prototyping this idea of going from a single dimension to a multiple resource dimension during EVM execution. Of course, the gas metering part is also a big part of the execution clients, and so it's important to prototype this and make sure that we can do this big change. Then there could be some attack vectors related to base fee manipulations, which we also need to look into. And finally, this is the part that might be more interesting to the audience here, which is everything on the user side remains the same, but for block builders now, the problem is a bit more complex, because now you don't only need to optimize for MEV and fees, but you also have this third dimension of packing the block in ways that allows you to put more transactions in. So maybe there's like now three transactions in your mempool that could fit, but one is more efficient than the other based on the resources you are already used in your block or the resources you have available. So if you want to know more, we have here some links for our analysis and our posts, both for the empirical analysis I showed and also for the proposal itself. Of course, you can also reach out to me. I'll be around and happy to discuss. If you see any concerns with these or have any questions, just reach out. And yeah, if you have any questions, I'm also happy to answer them. Thank you.
You wrote in the end that you're looking into making gas per resource also optimized per block. So if a certain block is using more storage, then the base fee for storage would go up and not necessarily for compute. I'm hoping I understood correctly the second point.
No. So so this is that part would be the pricing, right? Like we are going from a single dimensional pricing to a multidimensional pricing. This proposal is not touching on pricing. It's just saying we are changing the way that we say how full a block is, but that doesn't have any impact in the fees itself. The only change is now, actually, if you assume that demand remains the same, for instance, now base fee will be a bit cheaper because your block will be less full. So that would have an impact on the base fee for the next block. But if the demand would then pick up again and you would hover around on the target, it wouldn't have any change on transaction fees.
So my question is, do you have any idea on how actually modifying the price also, not only the amount of gas used, might affect how full blocks and how profitable they'll be?
So there's a few ideas of how to do multidimensional pricing. The simpler one is just to have a base fee type mechanism that is independent on each dimension. But I think the concerns there is that now for the user is harder because now you have to define your fee at each dimension. You could say maybe you can abstract that away, wallets can do that for you, but this doesn't solve the problem that now the protocol itself is more complex for users, and there's a trade-off there, right? But I think at the end, it's like, this proposal is something that you need if you want to do multidimensional pricing, because a middle step there is multidimensional metering. You need to at least meter those resources. And so this is a proposal that is in the middle path between the pricing, that doesn't have the concerns that pricing has, but still gives you some nice things. Thank you.
Right, thank you.